Okay, well, today we will I will introduce the topic of neural networks, okay? So on Wednesday, we wrapped up gradient descent for linear regression, and we said gradient descent is a way for us to find the minimum of a function just by taking small steps downhill, okay? Because earlier we said, with linear regression we can solve for where the gradient is equal to 0, and that's going to be a minimum. Here we're going to do gradient descent, which is trying to find the minimum just by taking small steps downhill, okay? So we said gradient descent can be used to minimize a function, okay, by taking small steps downhill. Okay, and now we will just make the function a little bit more complicated, another application of gradient descent. And this will be neural networks. Okay. And I'm going to, I don't know if you guys watched the YouTube playlist by Welch Labs, but I'm going to kind of just follow the example that, that exists in the Welch Labs video. And we'll kind of explore those a little bit deeper here. And again, you can rewatch those videos. And the hardest video is probably the back propagation video, but that's okay. All right, so we're going to say we've got inputs. Inputs will be our matrix X, and our output will be Y. Okay, and the variables are hours of sleep and hours of study, and these are the scores on the exam. And who knows? These are just made-up data points, but we will say 3, 5, 1, and 2, and the scores were 75, 82, and 93. And we want to know if we have a new point. Okay, so this is our training data. This is the data. We have the inputs and we have the outputs. Inputs and corresponding outputs. Okay, and we will use this to, quote, train our network. Okay, so we use this to try to get a network that performs well. And because we have the outputs, we would call this a supervised learning because the outputs are known. Okay. Output values for training cases are known. And we would call this regression because we're predicting a kind of a numeric variable. And if it was a categorical variable that we're predicting, it would be classification. So those are kind of your big over buckets of, I don't know, machine learning methods. They're a classification or a regression method, or supervised or unsupervised. Okay, so here it's supervised and regression. And then we would have some kind of test case, right? And this is our test case where we have the inputs, but we don't know what is the output here. This would be our test case. Okay, and the way the neural network works is we say, okay, well, how many inputs do we have? Well, we have two inputs, right? We've got x1 and x2. We have three cases, but each case there is an x1. This will be hours of sleep, and over here x2 will be hours of study. We have two inputs, and then we have, is that it? The output y, okay? Our output is our score. That's our y, okay? And the way the neural network works is we take our inputs, and then we go through kind of this, we have something called a hidden layer. And we might have some arbitrary number of nodes, and here we'll just put in 3, and all we do is we just take our inputs and we feed the input into all 3 nodes. Okay? We feed both inputs into all 3 nodes. And then these 3 nodes all output and get fed into this last node, okay? And this is supposed to simulate the way, you know, a brain works, where you have these neurons that have kind of synapses coming in, and then whatever, something happens inside that neuron cell, and then it sends a synapse out, okay? And this is kind of our, we're going to just start with this basic, what we might call a forward feed neural network. This is kind of the most basic neural network that we could have. This is not a course on neural networks, so as far as things go, we're just going to cover this basic forward feed neural network, but it's still pretty interesting in my opinion, and we can still do quite a bit with it. And then if you're like really into this, you can explore and learn more on your own. And you know, there's, if you learn Python, you can learn like TensorFlow, and that's like more neural network stuff. And anyway, okay. And then this whole concept of deep learning is just having a whole bunch of these hidden layers. So here we just have one hidden layer, and I think that's enough for us. But you know, you could take, you know, the input, and you could have, you know, multiple hidden layers of a whole bunch of different nodes, and you know, you'd have all these neurons and all these connections, and right. And so as you have many layers, well, this suddenly becomes deep learning. And all of these things sound fancy, but and I guess at some point they are a little bit fancy, but the base concept in much of these things are not too bad, okay? And you know, if you understand a forward feed neural network and you can explain it well, I think potential employers might find that to be an asset that you have. Okay. So anyway, this is what we have. The inputs go in, you know, we do some stuff, and then we process, and then we go forward. Okay. So let me just kind of redraw this here. So this will be our input layer. So we've got our input layer, our hidden layer, and our output. Okay, it could be an output layer, but here it's just our score y. Our inputs, we've got x1, x2. Sorry, they're falling off the screen there. And again, we have hours of sleep and hours of study. And basically all we do, let's just take a look at this first one. We will call our hidden layer layer Z, and this will be our first node. We will call this Z1. Basically, all we do is we take our, I just want to redraw this a little bit. We just take the values that come in, x1 and x2, and we just multiply them by weights, okay? So we will have a weight going from x1 to z1, and so I'm going to call this weight 1, 1 to indicate that it is the weight from x1 to z1. Okay, and this over here will be weight 2, 1. It is the weight going from x2 to z1. Okay, I'm also going to put a superscript of 1 here because this is to kind of indicate this is our first weight matrix, okay? Because we will have another weight matrix coming. So this is, that would be our first thing, and this is all we're doing. And then the next node, Z2, maybe I'll just have a different color here, and in here we would just have, I should just have some nodes, weights going there, and over here we would have another set of weights. Here this would be weight 1, 2 in our first set of nodes, and this would be weight 2, 2 in our first set of nodes. Okay, and then you would have a third set of weights coming down here, and we would have weight 1, 3 and weight 2, 3 in our first set of nodes. Okay, this being Z3. Okay. And so all 6 of these weights would get arranged into a matrix. Okay, and so we would have a well, here, let me just, before I get there, let me just kind of illustrate what I'm trying to do. And so we would say that this value Z1 is going to be the product of x1 times weight 1, 1 in kind of our first weight matrix, plus x2 times weight 1, 2, okay? And then, Z2 would be equal to x1 times weight 1, 2 plus x2 times weight 2, 2. And then we would have Z3 would be x1 times weight 1, 3 plus x3 times weight 2, 3. Did I mess something up? Oh yeah, you're right. 2, 1. Thank you. Okay. So okay, so this is what we have, and then so once we get these z values, we throw the z values into a function, okay? The z value, so inside the node, so the node gets these inputs. Inside the node, we apply a function. Okay, and so we'll just do some function on z1, and the output of that we will call a1. Okay, and then we will apply the function to the value coming into z2, and that will be a2. We apply the function to z3, and that will be A3. Okay, so basically coming out of the function will be A1, A2, and A3, and then we combine those three output A's together, and they come together into our output layer for Y. So here we'll have another set of weights, and I guess I'll call this, this will be the weight going from, there's only one node here, so this will be weight 1, 1 here, but to distinguish that it's in the kind of our second weight matrix, we'll put in a super 2. This will be the weight going from 2 to 1. Maybe I'll use a different, well, it's fine. And then the weight going from 3 to 1 in our second weight matrix. Okay. So we take all of these output A's, and then we combine them together. So going into here, we will have we technically call this this is to indicate this is kind of our second layer. I'm going to just put in superscripts 2 here. And to say this is kind of our third layer, we'll have a Z, and this is going to be in our third one. And I could put a subscript 1, but there's only one node, so I'll just leave it as that. Okay, and so coming in together, we've got Z3, and this is going to be the sum of A1 times weight 1, 1 plus A2 times weight 2, 1 plus A3 times weight 3, 1. Is that okay? Okay, and then lastly, we apply the function to this last value Z3, and this will become our output, our Y hat. So kind of just summarizing everything. So each arrow is a weight indicating, you know, how much the output of the previous node counts towards the next node. Okay, and then at each node, we apply a function to kind of produce the output for the next layer. I'll just say to produce the output. Okay, so the inputs x1 and x2 go in, they get multiplied by weights, and so we got different weights coming in, and then at each node here we apply a function that produces a new set of values, a's. Those get weighted. They go now, those three weighted outputs come together into this node, and then this node applies a function, and that's how we get the output there. Okay, so can we kind of follow the, I don't know, at least where our numbers are going? Yes?
Are the functions that we apply each day, are they the same?
Yes, they are. They're going to be the same here. They don't necessarily have to be, but for simplicity, we like to keep things simple. This as simple as this is, but we like to keep at least the overall concept fairly straightforward and simple. And so we're going to apply a certain function. This is kind of we'll look at the traditional classical function, which we call the sigmoid function. That's going to be the function that we apply. But things have changed, and they now apply different functions here. Okay, is this okay? That took a while here. All right, so let me see what I can just copy onto our next slide here. Copy this. Okay, so we've got this, and that's not what I want. How do I? Just want to erase some of this stuff here. So this, all of this stuff with the X's and the W's, a lot of this can all be simplified with just some matrix notation, okay? So we will say, if we take a look at what W is, if we create a matrix W1, we will have a 2 by 3 matrix, okay? And then if we take a look at what Z ends up being, all this is we're just taking our input matrix X, okay? And each row, like here I've got three cases of 3, 1, 5, 1, and 10, 2, okay? This is basically X1 and X2, and I have 3 observations, right? That's why it's 3, but and so therefore when I do X times W1, this is basically N times 2. This is the number of observations with 2 variables, and W is 2 by 3. So this is number of X variables, and then 2 by 3 is X variables, and then the 3 is kind of nodes in the hidden layer. So the output, our matrix Z, which to indicate it's our second layer, Z2 will be N by 3. This is number of observations times number of nodes. So Z is a 3 by 3 matrix because I've got 3 observations. Okay, and if I had 100 observations, I would have 100 rows and 3 columns. Yes? Yeah, the number of nodes is arbitrarily chosen ahead of time. So here I said we're going to have 3 nodes. If I wanted 50 nodes in the hidden layer, I could have 50 nodes. If you want 100 or 10, whatever, it's arbitrary. Okay, we don't have good reasoning for how many nodes to select. Okay, so here in our case we will have a Z will be 3 by 3. Is that okay? So let me just kind of I'll just write all of this out here. So let me, so x is going to be n by 2. N will be number of training cases. Okay. Times W1, which is 2 by 3. And this produces Z2, which is going to be n by 3. Okay. We apply the function f to z, and this will produce our outputs A2. Okay, and this is also f just applies element by element, so this is still going to be an n by 3 matrix. Okay. We've got another weight matrix going from A2, and this is our second weight matrix. So to kind of represent the arrows. So A is n by 3. What do you think the dimensions of W are going to be? So keep in mind our network looks like this. We've got 2, we've got 3 over here, and then the output layer has only 1. So what are the dimensions of W2? 3 by 1, right? And then so this will produce kind of our third matrix, a matrix Z here, and this will be n by 1. Now we have one value for every input row. Okay? And then finally we apply a function to Z3, and then technically this could be A3, but we will just call it Y hat. This is going to be n by 1. Okay. And so this process of going from X and applying our matrices and functions, so there's really kind of just 1, 2, 3, and 4 things. This is known as forward propagation. But technically, we could just write this all as one function, right? We could just say y hat is equal, and we could just kind of say the function applied to Z3, but what is Z3? Z is A times W2. What is A? A is this. So if I kind of start over here, this is just kind of one big thing that I apply a function to, and then I multiply this by W2, right? So here we kind of just do one step at a time, but this could also be written this way. Is that okay? So when we talk about the output of a neural network, it's really just a slightly complex function, okay? But that's all it is. All we're doing is we're just taking our input x, we're just multiplying it by some weights, applying some functions, and multiplying by weights, and applying another function, so on and so forth, until we get, an output. And when we do this, we get, if we have n inputs with 2 x variables, and we get n outputs of just one prediction, that's what we have. Okay, so this is just a function. And so what we want to do is we want to measure how good is the fit between y hat and the actual values y. Okay? And so we're going to create a loss function here. So to train our network, we need a loss function to measure how good our predictions are. Okay, so all we're going to do is we will have the loss function L be kind of the total residual sum of squares. Okay, so we're going to take the output, the true outputs y, subtract off our y hats, and square that. Okay, and we can either say we can rewrite all of this. And A2 times W2 is equal to Z3, and F applied to Z3 is Y hat, or we could say Y hat is equal to F of X, it's getting messy, XW1 multiplied by W2 or something like that, right? So we could have it this way, and we can replace this with all of this. But basically, we're just going to measure the distance between here and here, square that. You don't have to rewrite all of this in your notes. And that's what we want to do, okay? So we want to minimize our loss function, right? What are the things that we can alter? We cannot alter, if we look at this, we can't alter our inputs x, okay? So that's because those are fixed values, right? So we cannot alter x or y, okay? But we can alter the weights, right? We can alter the weights in matrix W1, our first weight matrix, and our second weight matrix. So we can alter those weights. So what we want to do is we want to find the gradient of our loss function with respect to W1 and W2. Okay, W1 has 6 weights. W2 has 3 weights. Okay, because W1 is a 2 by 3 matrix and W2 is a 3 by 1 matrix, right? So we've got a total of 9 weights to kind of alter and figure out. And all we're going to do is just do this total sum of squares things. We're going to find the gradient of this. And to minimize, so the big picture idea here is we can just start off with some arbitrary set of weights. We've got 9 weights. We'll just start off with an arbitrary set of weights. We're going to find the gradients. And we just take a small step downhill. Okay? Then we recalculate our gradient. And then we take another step downhill, and we just keep doing this over and over and over. And gradient descent says if you keep walking downhill, eventually you'll reach the bottom of the hill. And so when we do that, we should get something that has a very small loss value. Okay, and a very small loss value would indicate to us that our predicted values y hat are going to be close to the actual values of y. Okay, so that's what we want to do. Okay, so in order for us to do this, we've got to do some calculus and taking derivatives. I should talk about this function f. Okay, so just a note about the function f. Okay, we call this the activation function. It's just a fancy name for taking the function f. And really, what this is, this is known as what we're going to use is we will use the sigmoid function. And what a sigmoid function does is it takes the domain of the sigmoid function is negative infinity to positive infinity, but its output range is 0 to 1. So it just basically squishes everything from minus infinity to positive infinity and just squishes it to 0 to 1. Okay, so the way it looks is it looks like this. Something like that, okay? It's a little bit more curvy. This looks almost like it's flat, but it's hard drawing. No sympathy from you guys. But it's supposed to, okay, I can't do it, but just go on Wikipedia and look up sigmoid function. You'll get a better picture, okay? Here, I'll just do that right now. Here we are. Okay. Ta-da, this is what I wanted. Ah, of course. All right, well. Okay. Just pretend I drew this beautiful curve here. And, okay. Why is it transparent? Okay. All right, anyway, all right. So just pretend I drew that, and it just goes from, you know, it looks like that. The function is defined as this, 1 over 1 plus e to the negative t, okay? So that for very large values of t, this value becomes very close to 0, so you get 1 over 1. And then for very negative values of t, this becomes like 1 over 1 plus a million, okay? And so you get values very close to 0. Okay, this is the sigmoid function. It's like the inverse of the logit, okay? Okay, and so we're going to run out of time here, but so on Monday, you know, we will find the gradients. Hang on, you guys are packing up. Okay, we will find the gradients of our loss function with respect to the two weight matrices. Okay. Hang on, you guys. You guys can pack up, but just be quiet. So we're going to find the gradient of our loss function with respect to the two weight matrices. What this will allow us to do is it will allow us to then use gradient descent. We can then use gradient descent, so just so we don't lose sight of the big picture, okay? use gradient descent to find the values that should go in W1 and W2 that minimize the loss function. Okay, so we can then use gradient descent to find the values of our weight matrices W1 and W2 that minimize the loss function. Okay, and then when we minimize the loss function, then that means, you know, our predicted values are close to the actual values. Okay, so minimized loss function means predictions are close to actual values, which is what we desire. This is where gradient descent comes in very handy, is because with a lot of data, or, you know, as our network grows and gets bigger and we have more and more W's to calculate, it's no longer going to be possible to just calculate the gradient and set the gradient equal to 0 and solve. Okay, that was possible for linear regression, but it's no longer feasible for a complex function like this. So we find the gradients. We can't set it equal to 0 and just solve for the minimum, but we find the gradient and we can just use gradient descent to just keep walking downhill to get us to a minimum. Okay. All right, so that's what we'll do on Monday. Get ready to do a lot of matrix calculus and derivatives, and we'll get to see how this works.